So now that we've talked about properties of logs, let's go ahead and figure out how to actually evaluate them and come up with numbers. So this is section 4.4, and it's called Evaluating Logarithms and Change of Base Theorem. Now, a couple things before we get started. You will need a calculator for today's lesson. One thing is, in your calculator, you have this symbol. This symbol actually means the square root of a number. What number times itself twice gives you the radicand. But we know that that button automatically means we're looking for the second root. Your calculator has a button that looks like this. What that actually means is this means the log base 10 of whatever the number is. This is called a common log. And we'll see some more use of this in the upcoming sections. But for right now, it's important that you know that if there's no base written, it's automatically assumed to be base 10. And close to where the log button is, you'll see an ln button. And what ln means is this means a log with base e. This is called a natural log. Now, natural log is, you might think, why isn't it NL instead of LN? It's Latin. So Logarithmia naturale or something like that. But that's natural log. All right. And then we actually have this property. I don't want to get too into it right now, but just like you could take the square root of both sides, just like you could take, you can multiply both sides by a number. If you have a problem where it's 2 to the x power is equal to 5, that's an exponential equation, and we said that the way that you solve a problem like that is we use logs. Logs are the inverse of exponential functions. So we could actually take the log base 10 of both sides. By taking the log, we could actually bring that x down. This is using the power property. And then log 2, you could just type in your calculator. We know log is really log base 10. So in your calculator, you could just type in log of 5 divided by log of 2. Now you don't have to say log base 10. If you say log, it's assumed to just be base 10. So you could type that into your calculator. And let's see what I get here. So log 5, close parentheses, divided by log 2, close parentheses. This comes out to about 2.3219. Now with logs, you want to round to the 10,000th place, which means the 4th decimal place. It goes tenths, hundredths, thousandths, 10,000ths. So with logs, we always round to the 10,000th place. But I want you to notice this step right here. You see how we have, just kind of keep an eye on this right here. Another way I could have written 2 to the x power is equal to 5 is I could have written log base 2 of 5 is equal to x. And then you could see the base there is really 2, but writing it in exponential form using the translation property and then going all the way to the answer, I want you to notice where the argument is 5, and I want you to notice where the base is 2. Let's take a look at one more example, and then I'll show you the theorem. I don't just want to show you something and tell you to memorize it. I'd rather you see where it comes from. What if we had the log base 3 of 7 is equal to x? Well, just like in the last example, we could write it in exponential form. 3 to the x power is equal to 7. We could take the log base 10 of both sides, bring the x down using the power property. X times the log of 3 is equal to the log of 7. Divide both sides by the log of 3, just like we did in the last example. And we get x is equal to the log base 10 of 7 over the log of 3. So again, take a look at what we started with and notice where the argument is and notice where the base is. Just to finish this problem, if we type in log 7 divided by log 3, we'll get the answer is 1.7712. So what the change of base formula says is we don't have to do these steps over and over again. That's unnecessary. We could see a pattern here. If we generalize this pattern and we use variables instead of numbers, look what happens. The log base b of a is equal to x turns into the base to the x power is equal to a. Taking the log of both sides, we could bring the x down. And this is actually the change of base theorem. What the change of base theorem says is no matter what base you start with, you could convert it to a common log and just simply use this. So let me write it out. If we have log base, any base of a, on your calculator, if you want to figure out what that number is, that's always going to equal the log of the argument divided by the log of the base. That's what we showed over here. This is called the change of base theorem. So let's do some examples with this just to practice. I'm going to ask you to evaluate. Let's say log of 5 plus log of 7. Now, we could do each one individually, but notice that there is a plus sign in between, so we could use the product property. And product property says if we see plus between logs, we could actually multiply the arguments. So this is just log base 10 of 35, and we could just type that into our calculator. Log base 10 is really just regular log, and 35 gives us an answer of 1.5441 if we round to 4 decimal places. What about if we had, what if we just typed in the log base 10 of 35? What I mean is, what if we use the change of base formula? Well, this would be the log of 35 divided by the log of 10, right? Now the answer would be, if you type this into your calculator, log 35 divided by log 10 is exactly the same number, 1.5441. So the question is, why is that? Well, going back to our discussion of logs, remember, if there's no base written, it's automatically 10. And this is the inverse property of logs. I'm going to go back in the notes just to show you this. And if we go back to our properties of logs, let's see here. Right here, the inverse property. We're taking the log base 10 of 10, and you could see that they would just cancel. So that's really what's going on for this problem. Log base 10 of 10, this actually just cancels, and you're just left with 1. So it's log of 35 over 1, which is the same as the problem above it. What if we had the log base 2 of 8? Well, we could just type into our calculator log of 8 divided by log of 2. And I'd recommend you actually type these into your calculator too. It's good to practice opening and closing the parentheses. So we're going to have log 8 divided by log 2. And this just comes out to be 3. Just kind of an interesting point. The reason why that's 3 is, remember, this is 2 to what power is equal to 8. 8 is 2 to the third. So you can see how that works. Another thing is, yeah, I think that pretty well explains why it's 3. So let's go to the next problem. What about if I asked you to figure out the log base e of 5? Well, we have a couple different ways we can handle this. One way we can handle it is using the change of base theorem and just type log 5 divided by log e. But remember what we said log e was. We said log e was the natural log. So it's a little bit faster just to type in ln, and that's what you should do. So the natural log of 5 is just 1.6094. But you could see it, you also get the same answer if you type in log 5 divided by log of e. Now some of your calculators might say e to like a power. You just put the power as 1. And you do get, of course, the same exact answer. One more problem, how about something like this? What if it was the log base 10 of 2 times 10 to the 5th? Well, I mean, we could just type this into our calculator, right? Type in log of 2 times 10 to the 5th divided by just log 10, or remember, we don't even need that 10 there. I mean, we could just type into our calculator just this problem as it is, log of 2 times 10 to the 5th. Because we know log base 10 is really just 1, right? So that wouldn't even be necessary. So let's see what this is. Log of 2 times 10 to the 5th. No matter which one you type in, you will get 5.3010, and that's our answer. Okay, just want to make sure that I'm clear here. So using the top technique, it's the log of the argument divided by log of the base. The base was 10, so the reason why that's not necessary is because if it's not written, the base is 10, right? So that's why log base 10 of 10, that would just cancel, which is why the second technique is just a little bit faster. All right, thank you very much. Stay tuned for our next lesson.